Imagine a clear raindrop falling onto a mountain, yet ending its journey with the salty taste of the ocean. That drop carries no salt from the sky, but along the way, it quietly collects memories from the rocks. An average liter of seawater contains about 35 grams of dissolved minerals invisible to the naked eye. The immense body of water covering most of the planet is salty, from coastal shores to the darkest ocean trenches. Every day, sunlight lifts enormous amounts of water into the atmosphere, yet almost all the salt remains behind. By simple logic, salt keeps entering but rarely leaves, so the sea should become infinitely saltier. After billions of years, the ocean should be thick with minerals, no longer resembling the blue water seen today. If rivers stopped carrying minerals, the sea's chemical composition would gradually lose an important source of replenishment. If evaporation and rainfall were disrupted, salt would be redistributed, causing many marine regions to change rapidly. Even a small change in salinity can affect water density, currents, and the survival of marine organisms. Yet the ocean has not become a thick salt basin, nor has it lost its salty taste over time. Minerals continue entering the sea while also becoming trapped in sediments, organisms, and newly formed rocks. This stability is not stillness, but countless flows of matter quietly pulling against one another. Every drop of seawater resembles a tiny page preserving traces of mountains slowly worn down by rain. This is the ocean, Earth's mineral ledger, recording an exchange that has continued for billions of years. The story begins when Earth was still hot, its surface constantly reshaped by impacts and volcanic activity. Water vapor escaping from the interior accumulated in the atmosphere, waiting for the planet to cool enough for prolonged rainfall. As temperatures fell, water collected in low basins, forming primitive oceans across the planet's young crust. Those earliest waters did not immediately resemble modern seas. Their composition changed alongside the rocks and atmosphere. Hot water touched newly formed rock, dissolved many elements, and carried them into the growing ocean basins. Below the seafloor, water entered hot crust, reacted with rock, and returned carrying dissolved minerals. Volcanoes also released gases and material, but they were only one part of the ocean's salty origin. A more persistent source appeared when rain began attacking the rocks exposed across the continents. A raindrop absorbs carbon dioxide, becoming a very weak acid that is still strong enough to affect rock. Through repeated soaking, flowing, and freezing, bonds inside rocks weaken and release mineral ions. Weathering does not destroy mountains instantly. It works through tiny changes repeated over immense periods. Groundwater continues reacting underground, collecting minerals before reappearing at springs and streams. Small streams merge, turning material taken from rocks into invisible passengers carried by rivers. Rivers carry more than visible mud. Most of the salinity story lies in substances already dissolved in the water. Sodium, calcium, magnesium, and many other ions leave the continents, even though river water still tastes nearly fresh. River minerals remain dilute because new rainwater continually mixes into the flow on its journey toward the sea. River water stays in motion briefly, while many ions remain in the ocean for far longer. Therefore, tiny mineral loads from individual rivers can build a major chemical signature when combined over time. As rain, wind, and temperature wear down the continents, the ocean's mineral ledger receives new entries. The foundation of salinity was established. Rocks supplied minerals, water transported them, and the ocean became their gathering place. The system's first response was not to keep every mineral, but to move them continuously through the water cycle. Water evaporating from the sea is nearly pure because salt ions cannot easily escape with the vapor. Water vapor forms, clouds, moves inland, and falls again, beginning an entirely new cycle of rock weathering. Each cycle returns fresh water to the continents while leaving most of the old minerals in the ocean. This is the simplest trap. Water escapes, while dissolved substances remain inside the ocean basin. However, the open ocean does not dry up like a closed lake because rain and rivers continuously return water. Waves and tides mix coastal waters, preventing riverborne minerals from remaining permanently near the estuary. Ocean currents spread them farther, turning countless small continental sources into part of one shared ocean. Some ions react together, form solid minerals, and sink instead of remaining dissolved. Others are absorbed by organisms to build shells, skeletons, or maintain essential biological functions. When organisms die, some of their minerals become sediment and are gradually buried beneath new mud. Young seafloor continues exchanging elements with seawater, both adding new substances and trapping older ones. The ocean does not merely receive minerals, it also processes, redistributes, and removes portions of them. This process is so slow that a human lifetime sees only waves, not the chemical ledger changing underneath. In the early ocean, life had to adapt to water containing increasing amounts of dissolved ions. Early cells had to regulate water and salts across their membranes, or their internal balance would quickly collapse. The ability to regulate salt became a basic requirement for life to survive in seawater across generations. Different species gradually occupied salinity zones suited to them, from unstable estuaries to relatively steady open seas. Salinity, therefore, became more than a geological result. It became a powerful ecological boundary. From scattered reactions, Earth gradually developed a vast cycle that keeps water and minerals moving. Each watershed became a collection network, carrying water from mountain slopes, forests, and plains toward the sea. Rock type, rainfall, and vegetation determine the particular mixture of minerals carried by each river. In regions of easily dissolved rock, water gathers minerals faster than in areas built from resistant stone. Plant roots hold soil in place, but also release substances that assist weathering, drawing biology into the salt journey. Soil acts as a temporary storehouse, holding ions until later rain carries them into rivers or groundwater. Groundwater may remain underground for years, dissolving rock before entering rivers or flowing directly into the sea. At an estuary, lighter freshwater often rests above denser seawater, creating a constantly shifting mixing zone. Tides push seawater upstream, then river flow pulls the mineral mixture back toward the ocean. Fine estuary mud absorbs some substances, so not every ion from the mountains immediately reaches open water. The remainder passes the river mouth, joins coastal currents, and spreads toward more distant regions. Wind pulls the ocean surface, while Earth's rotation bends the flow into enormous circulation systems. These circulating systems mix salt horizontally, preventing minerals from remaining concentrated near one continent. Storms stir the surface layer more deeply, pushing salinity differences downward instead of preserving them unchanged. In calmer regions, waters with different salinities can settle into more stable layers. Colder or saltier water is usually denser, so it tends to sink beneath warmer or fresher water. This rising and sinking connects ocean layers and helps form the circulation network that transports heat around the planet. Salinity is therefore shaped simultaneously by rain, evaporation, rivers, melting ice, and moving currents. Where evaporation exceeds rainfall, surface water is often saltier because water disappears while salt remains. Where rainfall or river input is strong, surface water is usually fresher even though salty seawater remains below. Enclosed seas with weak exchange can develop salinities very different from those of the open ocean. If water leaves mainly through evaporation, closed lakes can accumulate salt much faster than the ocean. The ocean avoids that fate because of its enormous size, constant mixing, and multiple pathways that remove ions. Some elements remain dissolved for very long periods, while others are quickly captured by organisms or rocks. How long an ion remains in seawater determines how strongly it can accumulate and spread across the ocean. Ultimately, incoming and outgoing flows create a dynamic balance that keeps global salinity within a relatively stable range. To understand the true mechanism, one must examine how water can pull charged ions away from rock. A water molecule has electrically different ends, allowing it to surround and separate charged particles. When enough water molecules pull from several directions, an ion can leave the crystal lattice and enter the flow. Weak acids in rainwater accelerate this process by reacting with minerals that are easier to break down. Rock does not transform directly into table salt. It releases many ions that then follow different chemical paths. Among them, sodium often remains in seawater for a long time because organisms and sediments remove it slowly. Chloride also comes from rocks, volcanic gases, and seafloor interactions, and commonly combines with sodium. Sodium and chloride make up most dissolved material, creating the familiar salty taste but not the ocean's entire chemistry. Magnesium, calcium, potassium, sulfate, and many other substances help shape chemical reactions and marine habitats. Total dissolved material determines salinity, while the proportions of individual ions shape seawater's distinctive properties. When seawater evaporates, water molecules escape from the surface, while dissolved ions remain held within the liquid. Because water is lost without a matching loss of salt, the remaining water becomes more concentrated during hot, dry periods. When rain or rivers return water, concentration decreases, creating a continuous rhythm of concentration and dilution. Rivers still contain salts, but fresh inflow and short residence times keep concentrations far below those of the sea. A river water molecule may quickly reach the sea, while an ion can remain through many cycles of evaporation. That is why many freshwater rivers can feed a salty ocean without becoming as salty as the ocean themselves. Salt does not simply remain suspended. Some ions constantly exchange with the surfaces of mud and clay particles. When mud sinks, it can carry dissolved substances downward, temporarily removing them from the water above. Over time, sediment layers thicken and lock part of the chemical record into rock beneath the seafloor. Tectonic motion can drag those rock layers deep underground, removing minerals from the ocean for long periods. Elsewhere, hot material rises from Earth's interior, reopening part of the mineral matter buried below. Hydrothermal vents do not only add substances, hot water can also remove certain ions from seawater. Seawater enters cracks in the rock, heats up, reacts, and returns like a natural chemical filtration system. Coral reefs and plankton also take calcium ions from seawater to build their hard structures. As shells and skeletons accumulate, they can form new rock layers that keep minerals out of seawater. The ocean is therefore both a place where minerals dissolve and a factory that creates new mineral solids. If incoming minerals exceed removal for a long period, salinity rises. The opposite imbalance causes it to fall. Yet this balance does not operate over days or years. Many reactions reveal themselves only across geological time. Relatively stable average salinity does not mean that every part of the ocean contains the same amount of salt. Near the equator, heavy rainfall can freshen the surface even when temperatures and evaporation remain high. In dry subtropical belts, evaporation often exceeds rainfall, making surface waters saltier than the global average. Near the mouths of great rivers, fresh water can create broad, low salinity zones extending far offshore. When sea ice forms, most salt is expelled, making the surrounding water denser, saltier, and heavier. That dense water sinks, helping carry oxygen and surface properties into the deep ocean. When land ice melts, fresh water entering the sea can reduce surface salinity in nearby regions. Salinity differences can create stable boundaries that keep surface and deep waters separated for longer periods. Strong winds, waves, and currents break those boundaries, but the amount of mixing varies from region to region. This imperfect mixing creates a rich map of salinity instead of a perfectly uniform ocean. The real question is not only where salt comes from, but how it is transported and removed. Today's salty ocean is a temporary result of a reaction network spanning the planet and reaching the seafloor. This balance does more than create a salty taste. It controls where many organisms can feed, grow, and reproduce. Marine organisms must constantly regulate how much water enters their bodies and how many ions cross their tissues. If conditions change too quickly, they must spend more energy maintaining their internal balance. Eggs and larvae are often more sensitive than adults, so salinity shifts can affect an entire new generation. Estuaries are especially fragile because salinity changes with rain, tides, dry seasons, and upstream river flow. When river flow weakens during the dry season, saltwater can move farther into estuaries and deltas. Freshwater routes, farmland, and drinking water supplies may come under pressure when salt intrusion continues. Offshore, salinity helps determine water density and therefore influences how ocean currents form. If salinity changes together with temperature, sinking rates can shift, and the wider circulation network can respond. Ocean currents transport heat, so density changes can influence weather and climate far away. An overly fresh surface layer can become stable and block nutrients from rising from deeper water. If mixing weakens, surface plankton may lose access to the nutrients they need to grow. Conversely, extreme evaporation in an enclosed basin can push salinity beyond the tolerance of many species. Only specially adapted organisms survive in hypersaline water, where maintaining water balance is a constant challenge. Salt also lowers the freezing point of water, changing how sea ice forms and melts. As sea ice forms, expelled brine can create unusually cold and dense flows near the seafloor. These changes may occur far from human settlements, yet their effects still travel through water and atmosphere. Along coasts, sea level rise and groundwater extraction can push the saltwater boundary farther inland. Once saltwater enters an aquifer, it is difficult to remove because the salt does not vanish when flow direction changes. Desalination can produce fresh water, but it requires energy, equipment, and careful handling of concentrated brine. Concentrated brine must be dispersed carefully to avoid creating excessively salty zones near the seabed. Salt is essential to marine life, but too much or too little can turn familiar habitat into a barrier. The ocean's mineral ledger is therefore also a record of the survival limits of countless species. Any major change in rain, ice, or river flow can write a new chapter into that record. To reveal how fragile this network can be, one raindrop will now pass through an extreme but plausible journey. A heavy storm strikes a mountain after the dry season, awakening cracks filled with accumulated mineral dust. The drop slips across the rock and dissolves a sodium ion locked inside a crystal for a very long time. From that moment, water and ion no longer share the same fate. Water can escape, while the ion remains. Muddy water races down the valley, carrying visible sediment and dissolved minerals hidden from sight. As the flood crosses the plain, some mud settles, but the sodium ion continues downstream. The rain ends and the river shrinks, yet minerals collected across the watershed are still moving toward the sea. At the estuary, floodwater creates a broad, fresh surface layer and pushes the salty boundary farther offshore. Many estuary organisms move towards suitable water because their environment changed after a single storm. The sodium ion passes through the mixing zone, enters a coastal current, and begins a far longer journey. Over the following days, wind and waves mix the surface water, gradually erasing the river's original signature. The water molecule that carried the ion may evaporate under sunlight, leaving the mineral behind in the sea. The vapor becomes cloud and returns inland, but the sodium ion has already been left for another cycle. The mineral no longer belongs to the mountain or the river. It has become part of the ocean. An ocean current carries it away from shore through waters of different temperatures and salinities. It may pass through an organism, but sodium is usually released back rather than stored permanently. It can attach to a clay particle, sink to the seabed, and later be lifted again by a bottom current. The journey may continue until surrounding water sinks and carries the mineral into the deep ocean. In darkness, it drifts above abyssal plains where continental material settles in thin layers. Near a mid-ocean ridge, hot water rising from new rock begins altering the chemistry of the surrounding water. The sodium ion may remain dissolved while other ions react, precipitate, and attach to a vent chimney. This reveals the central secret. Every ion follows a different path and remains in the ocean for a different time. The ocean does not retain every mineral equally. Reactions, organisms, sediments, and crust selectively remove them. If rivers delivered salt without any removal pathways, today's ocean would look radically different. But if mineral inputs disappeared entirely, ongoing removal reactions would still gradually change seawater composition. Salinity survives through two-way movement, not through a salt reservoir that only accumulates. To monitor this balance, scientists measure salinity at many depths and across many parts of the ocean. Sensors lowered into the sea record temperature, electrical conductivity, and pressure to estimate salinity. Depth measurements reveal that water layers appearing similar at the surface can have different histories and densities. Autonomous floats drift with currents and repeat measurements where research ships cannot visit regularly. By repeatedly rising and sinking, they assemble a broad picture of temperature, salinity, and ocean movement. From space, satellites observe tiny surface changes to estimate salinity across enormous areas. Satellites do not taste seawater. They measure microwave signals influenced by the salt content near the surface. Measurements from ships and floats are used to verify, calibrate, and interpret observations made from orbit. Long data records reveal which regions are freshening, becoming saltier, or shifting with the seasons. When combined with rain, wind, and temperature, salinity becomes a trace showing where a body of water has traveled. At estuaries, monitoring stations track the salt boundary to support water management, farming, and ecosystems. When saltwater advances, adjusting water intake timing can reduce pressure on fields and freshwater supplies. Coastal wetlands are protected because they slow water, trap sediment, and provide shelter for wildlife. In laboratories, Organisms are observed under different salinities to identify the tolerance limits of each species. This knowledge helps predict which species may move, decline, or expand as coastal conditions change. Ocean models combine temperature and salinity to recreate how water sinks, rises, and transports heat. When models and observations disagree, the difference can reveal a current or water source not yet understood. Salinity, therefore, becomes an investigative tool for tracing the origin and journey of individual water masses. It reveals where water was lost through evaporation, added by rainfall, or supplied by melting ice. From a familiar taste, salinity has become a vital signal for reading the movement of the planet. The first misconception is that the sea is salty because a gigantic salt deposit dissolved beneath the seafloor. In reality, salinity comes from countless small sources and long-running reactions, not one enormous salt mine. A second misconception is that rivers contain no salt because most river water does not taste noticeably salty. Rivers do carry dissolved ions. They are simply more diluted and do not remain long enough to accumulate strongly. A third misconception is that the ocean must continually become saltier because rivers keep delivering new minerals. That input is real, but sediments, organisms, and seafloor reactions also continuously remove material from seawater. This does not hold salinity perfectly fixed, but it prevents endless increase through simple addition. Another misconception is that all seas have equal salinity, despite major regional differences in climate and freshwater input. Dry enclosed waters are often saltier, while river mouths, rainy regions, and melting ice zones are usually fresher. Salt does not rise into clouds with water. Most of it remains behind when water molecules escape the surface. Rain can carry dust and airborne sea salt particles, but this is not the main source of ocean salinity. The sea is not salty simply because it was meant to be. Salinity was built and maintained through geological time. The modern turning point is realizing that salinity records not only the history of rocks, but also today's climate. A region becoming saltier may indicate stronger evaporation, while freshening can reflect added rainfall or melting ice. Global salinity maps help track the water cycle in ways that land-based rainfall measurements alone cannot. Small surface changes can signal future shifts in currents, ecosystems, and rainfall patterns. The goal is not to hold the ocean at one fixed value, but to understand the direction and speed of change. A naturally variable ocean can remain stable as long as change does not exceed the system's ability to adapt. Risk grows when rain, melting ice, river flow, and temperature change faster than deep balancing cycles. Reactions in sediment and seafloor rock are slow, so they cannot immediately offset short-term climate changes. Salinity, therefore, acts like a clock, comparing fast climate rhythms with the planet's slow geological rhythm. Monitoring salinity can help identify which estuaries, fisheries, and freshwater sources will face pressure first. It also reveals where surface water is separating from deeper layers, changing nutrients and oxygen. A tiny salt ion can therefore become a signal for processes far larger than the ocean carrying it. The ocean is no longer merely the final reservoir, but the exchange center connecting rocks, climate, and life. Understanding salinity means understanding how Earth moves matter, redistributes heat, and maintains habitable environments. The sodium ion that left the mountain long ago continues drifting, unaware of which current will carry it next. Behind it lie rain-worn cliffs, rivers, and countless completed cycles of evaporation. Each sparkling wave carries a dissolved fragment of the continents, recorded in the language of minerals. The sea is not merely water. It is the planet's chemical history, rewritten whenever rain touches rock.